Hello, many worlds. Good. I couldn't wait to actually do a basically a walk through these, and I'm really gonna just do the Hello Many Worlds for now. Just want to take a look at how this really looks like. I'm basically a noob in TensorFlow and machine learning. I haven't used TensorFlow before. I'm a noob in quantum computing as well, so it can be a funny video. Um, so it's really exploratory. I played with Cert before, and I have a basic understanding of quantum computing. Um, and quantum machine learning is still a bit, I'm still relatively uh, new to the whole thing here. So let's take a look at how, uh, you know, how does the whole thing look like, and what can you with that. It's been pretty loud in social media in the past day or two, and so I want to take a look at these basically. And so I've got a notebook ready here, and we're gonna go through these. So this tutorial shows you a classical Hello Many Worlds. By the way, that's a really nice it's a really nice title for this. So this tutorial shows how a classical neural network can learn to correct cubic calibration errors. It introduces Circ, a Python framework to create, edit, and invoke noisy intermediate-scale quantum circuits, and demonstrates how a circuit interfaces with TensorFlow Quantum. So we're going to learn how to correct cubic calibration errors. It's an interesting example because it seems pretty uh, it seems, I don't know, complicated. It shows how a classical neural network can learn to correct cubic calibration errors. Okay, so we got TensorFlow installed. After some space issues, we got it there. So we're now basically gonna. So what are we importing here? Let's create a new Python 3 notebook. We're gonna call it a Hello Many Worlds. Um, And what are we importing? TensorFlow Quantum Circ, SymPy, NumPy, and a bunch of visualization tools. Uh, ba -ba -da -ba -da -ba -ba -ba. We are now the basics. So Circ and parameterized quantum circuits. Before exploring TensorFlow Quantum, let's look at some Circ basics. Circ is a Python library for quantum computing from Google. Uses defined circuits. So I'm not gonna go through these links because I've taken a look at Cert before. I'm familiar with all that. So let's move on. Cert uses SymPy symbols to present free parameters. What are SymPy symbols? SymPy is a Python library for symbolic mathematics. Ooh, okay. So what is these? Maybe we can put these things side by side. Can we do that? Can we do that? Seems we can, yes. So this A and B are, what if I print A? Okay. The following code creates a 2-qubit circuit using your parameters. So let's take a look at these. What we've got? What have we got here? Circ grid qubit. Yeah, remember there was. I've been using Qiskit too much recently. So you create a grid qubit, and that's a grid of what, 1 by 2? No, what is that? Should probably refresh that. I said I knew the basics, but I definitely don't. Documentation. Circuit qubit 00. Tutorial. Create a circuit on a grid. Exactly, that was the whole thing here. So it's the length and the okay. qubits on the grid. So that creates basically 2 qubits. Circuit RXA on qubit 0, RYB on qubit 1, and then a C0 with those controls. Okay, well, I'll just keep an SVG circuit. So I'll just keep the details of these for now. It's something to recap, I guess. But basically, so we're here just creating a circuit with Qiskit. To evaluate the circuits, you can use the circ simulator interface or replace free parameters in a circuit with specific numbers by passing in a parameter resolver object. The following code calculates the row state vector output of your parameterized circuit. The row state vector output. Calculate state vector with A 0.5 and B minus 0.5. Okay, those being the parameters for the rotation gates. And here you have the simulate circuit resolver. Okay, final state. Simulate. I don't remember really any of that. State vectors are not. I don't remember any of the circ notation details. State vectors are not directly accessible outside of simulation. Notice the complex numbers in the output above. To be physically realistic, you must specify a measurement which converts a state vector into a real number that classical computers can understand. The circ specifies measurements using combinations of the Pauli operators x, y, and z. As illustration, the following code measures z and z0 plus half z0 plus x1 on the state vector you just simulated. What? Z expectation from wave function. What the? What is these? Qubit map Q0, Q1, 0, 1. So this is an observable or what? Circ ZQ0, Z0. And then these. And then expectation value, expectation from wave function. Qubit map. So we're measuring tooth. That's interesting. So that's definitely a really different approach to Qiskit. At least what I'm seeing here. You're basically defining observables, and then basically calculating the expectation of those observables. That's one of the things you can do with this expectation from wave function thing here. This is something that I really didn't touch at all because I did just VQE, the VQE tutorial. What's the evaluate the expectation of this Pauli string given a wave function? Compute the expectation value of this Pauli string with respect to a wave function. By convention, expectation value is defined for Hermitian operators, and so this method will fail if this Pauli string is non-Hermitian. Yeah, that's expectation value. Okay, interesting. Can you do something similar with Qiskit? Okay. Quantum circuits as tenses. Okay, so what are tenses? What are tenses? Because the expectation value here, I think that was relevant for some of the quantum machine learning algorithms. Okay. What's that, by the way? Like, if I open Quirk, Cert.com, and I open Quirk, and I do in a basically Rx of, of 0.5, and is it a B of minus 0.5? So it's a Ry of minus 0.5. Okay, so that does, and then a control knot, well, basically here. Okay, so a control knot would do that. Yeah, whatever. Whatever. Quantum circuits as tensors. Tensor quantum, TensorFlow quantum TFQ provides TFQ. So what is these TFQ converted to tensor? A function that converts Circ objects into tensors. This allows you to send Circ objects to our quantum layers and quantum ops. The function will be called on lists of arrays of Circ circuits and Circ Paulis. What is a tensor first of all? So TensorFlow. What is a tensor? I'm a total noob to these. A tensor is a generalization of vectors and matrices to potentially higher dimensions. Internally, TensorFlow represents tensors as n-dimensional. Okay, so this is okay. So tensors are higher dimensional matrices. Is a tensor. So basically, that's an object that holds what, all your data or input space or solution space or something like this. A tensor. So this is a tensor vector of dimension 6, tensor of dimension 6 and 4, tensor of dimensions 4, 4, 2. Okay, it's just a, so that converts, okay, so that converts the circuit. You can convert a circuit into a tensor, Okay. Is it just the encoding of the circuit, or what is it? Tensor shape, tensor D type. 1 and nothing. Okay. This encodes the Circ objects as TF string tensors that TFQ operations decode as needed. Okay, so this is just a format to pass things around within TensorFlow. Rank 1 tensor containing 2 Pauli operators. Rank 1 tensor. Okay, so tensor convert to tensor, tensor shape to batching circuit simulation. So this is really dense as a tutorial, to be honest. Bum, 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 bum. So this batching circuit simulation, TFQ provides methods for computing expectation values, samples, and state vectors. For now, let's focus on expectation values. The highest level interface for calculating expectation values is the TFQ layer's expectation layer, which is a TF keras layer, and its simplest. What are keras? TensorFlow keras. Okay, it's a high-level API for building and training deep learning models. Which is the TF keras layer, and its simplest form. The layer is equivalent to simulating a parameterized circuit over many resolvers. However, TFQ allows batching following TensorFlow semantics, and circuits are simulated using efficient C++ code. Create a batch of values to substitute for our A and B parameters. Okay, so this is the batch values. It seems fairly intuitive, but this is like, I think there's been a considerable amount of work on integrating all that stuff. I mean, and again, I'm a total noob with TensorFlow, machine learning, quantum computing. It's just, but I think I can intuitively follow this so far. So you're batching the value. So these are just random values that you're going to batch as different inputs to run our circuit through. Batching circuit execution over parameter values in circuit requires a loop. So we're looping, we're creating the resolvers, the different resolvers, and then we're simulating, and then we're appending the results. That's what we're doing. Okay, the expectation values. Okay, so those are the results. Good. The same operation is simplified in TFQ. Ah, okay. So TFQ, but what is this expectation thing? It says it's a keras, it says it's a layer. I really don't know much about that, so I probably shouldn't. What's a keras layer? Let's say an API. Keras layers are the fundamental building blocks of keras models. Layers are created using a wide variety of layer functions and are typically composed together by stacking calls to them using the pipe operator. Okay, so layers are the building blocks of models. So we've got expected TFQ layers expectation as in like a keras layer. And so far what this does is it symbol names A, B, symbol values, batch values. So what it does is it simplifies all the simulation, all this batch simulation. Okay. So we got the same values in here, which are obviously different than the ones here. And then, okay, so that's it for the part, for the basics, I guess. Hybrid quantum classical optimization. So now that you've seen the basics, let's use TensorFlow Quantum to construct a hybrid quantum classical neural net. You will train a classical neural net to control a single qubit. The control will be optimized to correctly prepare the qubit in the 0 or the 1 state, overcoming a simulated systematic calibration error. This figure shows the architecture. What is this? Command, that seems like a neural network. There's a bunch of rotations in here. And so this neural network, expected output loss, MSE. What is MSE? I'm assuming what this is trying to tell me is that we have a qubit that we want to set it to 1 or 0. There's going to be some sort of assumption somewhere, or some sort of simulated calibration error, and so this neural network is supposed to learn that error that behavior of that error, and so supposed to correct that by controlling what the parameters of some rotation gates seems like. Okay, even without a neural network, this is a straightforward problem to solve, but the theme is similar to the real quantum control problems you might solve using TFQ. It's for quantum control problems. Okay, it demonstrates an end-to-end example of a quantum classical computation using the TFQ layer's controlled PQC parameterized quantum circuit layer inside of a keras model. For the implementation of this tutorial, this architecture is split into 3 parts: the input circuit or data point circuit. The first 3 are gates. It's the input circuit. Okay. The control circuit, the other 3 gates, and the controller, the classical neural network, setting the parameters to the controlled circuit. Ah, okay. So that's what I was not reading this, so that okay. What is the input circuit though? The data point circuit. Okay, that's okay. So that's your state preparation circuit, and then what these 3 other gates are doing are okay. So they're gonna try to compensate for the error that you might experience after applying your actual circuit, which are the 3 gates. And so the neural network learns about the systematic calibration error and then applies these rotations in order to basically correct that. Okay, that's pretty cool though. The control circuit definition. So So this is the control circuit definition. So what is this control circuit? It's a learnable single P rotation as indicated in the figure above. This will correspond to our controlled circuit. So we've got theta 1, theta 2, theta 3 as symbols. Then we basically prepare a parameterized circuit that has these parameters. And it only works on 1 qubit. Okay. Yeah, that's it. Then the controller. So now we define a controller network. The classical neural network layers. So this, I have no idea what's this about. I have never done this before. It's the first time I do this, but this is supposed to be the classical neural network. So you're creating the neural network here with a couple of layers. I guess 2 layers. Two dense layers, whatever that means. Given a batch of commands, the controller outputs a batch of control signals. Given a batch of commands, the controller outputs a batch of control signals for the controlled circuit. Controller outputs a batch of control signals. Okay. TF. What is these? How is that? How is that outputting any control signals? Keras overview. Layers. Keras overview. A sequential model. In Keras, you assemble layers to build models. A model is usually a graph of layers. The most common type of model is a stack of layers. Okay, that's a stack of layers. Okay, so that's basically these stack of layers, 3 layers. Or 2 layers. You input and your command, and okay. But the controller is giving the commands or what? The controller is randomly initialized, so these outputs are not useful yet. So this initializes the controller. Connect the controller to the circuit. That's the interesting part. So how is this? It feels a bit surreal, but what is the... It's like, what am I doing? I don't know. It feels intuitive, but I just can't really process that I'm connecting stuff in here without having touched TensorFlow in my life before. The TFQ to connect the controller to the controlled circuit. Use TFQ to connect the controller to the controlled circuit as a single Keras model. See the Keras functional API guide for more about this style of model definition. Okay, so that's a special model here. We're using a model to connect the 2 things. So we're wrapping the 2 things into a model. So circuits input and commands input. Keras input shape, whatever that is. So what does this whole thing mean here? So we're defining the circuit's input, the command's input. This input is a simulated miscalibration that the model will learn to correct. Commands will be either 0 or 1, specifying the state to set the qubit to. Okay. Next, apply operations. This I'm not so sure I understand that. Input, Keras input. What is an so this is an input layer, I guess, right? Or what is TF Keras input? I have to admit the documentation is pretty cool. A Keras tensor is a tensor object from the underlying backend, which we augment with certain attributes that will allow to build Keras models just by knowing the inputs and outputs. Input is used to instantiate a Keras tensor. Shape, string, Circuits input. Ah, okay, so this is just a tensor. This is not a model or whatever. It's a tensor. It's like a multidimensional matrix. Okay, it's a tensor. Next, apply operations to those inputs to define the computation. Apply operations to those inputs. Apply operations, so tends to control commands input. What's happening here? So dense to controller. We are okay. Okay, so we're giving some data to the controller. The controller is in turn a model, right? It's a sequential model. Okay. I guess at some point we're gonna just basically feed the whole thing with a data set. So we're applying our commands input, which is commands input to the controller. Oh, sorry, commands input, not circuits input. So it's going to be either, that's a float, so it's going to be either 0 or 1, then expectation layer, model circuit, observe Z, expectation layer. What? Now packages computation as a model. So we're actually building a model? Okay, that's how we're building the model. That's how we're building the, so this is the basically TFQ layer for classically controlled circuits. Expectation layer equals, it's a control PQC. What is the control? Ah, okay, control. It's okay, it's a special layer. It's a controlled parameterized quantum circuit layer. This is the model circuit. This is the, what is these operators? Z qubit. This I don't know. The full Keras model is built from our layers. TF Keras model, the full Keras model is built from our layers. Okay. So the circuit's input, the commands input, these are the inputs, and the outputs is expectation, which is what we're building here, which is the expectation layer. And that is this Z in here, I guess. It's a bit weird how this is being defined though, honestly. Now I get into a data set, I see. Circuit's input is defined as a okay, that does not define example, that defines the shape of those Keras. So it's a circuit's input. It's a string. Then the circuit's input here. Okay, then the commands input. It's going to be a float, 0 or a 1. And dense 2 controller commands input TFQ layer for classically controlled circuits. The expectation layer. Yeah, I'm so lost with this. What are we doing in here? So operators controlled. So that's model circuit. Dense expectation layer. Okay, so expectation layer, whatever that is, control P, QC, we're saying the circuit's input is in here, which is a string. What is these? And dance 2, which is basically the controller. I'm very confused. But well, I guess I'll come back to this. We're building the model basically. This may require the system to install the GraphViews package. I don't know if I have this. Let's see. I should install that. Okay, but anyway, the model takes this model takes two inputs: the commands for the controller and the input circuit whose output the controller is attempting to correct. Commands for the controller is just a lot of stuff at once. The commands for the controller and the input circuit whose output the controller is attempting to correct. Okay. The data set. The model attempts to output the correct measurement of measurement value of z for each command. The commands and correct values are defined below. The command input values to the classical neural network. The desired z expectation value at the output of a quantum circuit. This is not the entire training set for the task. Each data point and dataset also needs an input circuit. Input circuit definition. Typo. The input circuit below defines the random miscalibration the model will learn to correct. Random rotations. Data point circuits. Convert a tensor. Okay. So we've basically, there are two copies of the circuit, one for each data point. So we've got two data points. So this is, okay, so this is supposed to be a set of circuits that kind of define the random miscalibration. Tensor shape 2 training. With the inputs defined, you can test run the TFQ model. Now run a standard training process to adjust these values towards the expected outputs. Model. The optimizer loss function. Okay, so here we're doing some standard ML stuff with a loss function, with an Atom optimizer, whatever that means, and then we're compiling the model, and then history model fit. So we're fitting these to the expected outputs. And now we are gonna plot the history. Learning to control accurate iterations. From this plot, you can see that the neural network has learned to overcome the systematic miscalibration from the roughly 5 iterations. Learning to prepare. What have I done? Okay, there's a lot of concepts I'm not 100% familiar with, so really know about all these. I was just curious, but so what I've done is, so we've peeled a controlled circuit, the model circuit. We've built a model that's a controller, Given a batch of commands, the controller outputs a batch of control signals for the control circuit. What are these control signals, though? Then we're connecting the things in a model. So we're connecting the controller, the neural network with the circuit, with the control PQC layer. Observes that. So this needs to be specified. Expectation layer. Dance 2 is the controller. I'm still not. I definitely have to come back to this. The controller commands input. Commands we add a 0, 1, specifying the state to set the qubit to. Okay, I'm not really familiar with TensorFlow, how these models are defined, how this all looks like, looks like, or why does this work at all. But I intuitively understand what's that we're doing here. So it's learn to control a qubit, as in like the expected. What are the expected outputs though? Where is it coming from? Expected outputs. The desired Z expectation value at an output of a quantum circuit is okay. Because the Pauli Z operator has the expectation values 1 and minus 1 for the classical 0 and 1, so to say. And see, so this is the expected outputs. This is the command that we're okay. But and what is the input circuit? Okay, so so this is the input circuit definition. Okay, so this is an input circuit that basically randomly miscalibrates, and then this whole neural network learns how to correct that. Okay, so the command tells, no, it should be a 1. Yeah? Or it should be a 0, or should be a 1, should be a 0. And then yeah, I think so. And then, but then how does the actual training happen? What is it that we're fitting in here? Data point circuits. Expected output. Commands. Just these values. With the inputs defined, you can test around the TFQ model, data point circuits, and commands. So is it commands that we're... Is it commands that we... That's the command. It's the commands that we're fitting, or what? Command inputs values to the classical network. These are the expectation values. I'll have to give it another round, definitely. Training, learning to prepare eigenstates of different operators. Okay, so now we're kind of generalizing and saying it's not just anymore about the Z state or the Z operator. We're doing all the operators. The choice of the plus minus Z eigenstates corresponding to 0 and 1 was arbitrary. We could just have easily wanted 1 to correspond to the plus Z eigenstate and 0 to correspond to the minus X eigenstate. One way to accomplish this is by specifying a different measurement operator for each command, as indicated in the figure below. A different measurement operator. So that's the part here at the bottom. This requires use of expectation of the TFQ layer's expectation. Now your input has grown to include 3 objects: circuit, command, and operator. Okay, so we're now going to generalize that new model definition. Let's take a look at the model to accomplish these tasks. Commands input, circuit, operators input. Those are the inputs to the model. The circuits input, the commands input. So you're learning the commands. No, you're training the neural network. I'm still confused what the commands are. That's what's confusing me. What are these commands? But anyway, so now we're adding the operators input here. Here's the controller network. The controller network. Or the network is the input. Or I don't know. Combine the circuit and the controller into a single Keras model using TFQ. So now, since you aren't using a PQC or a control PQC, you must append your model circuit into the data point circuit tensor manually. Okay, and now but why aren't we using the PQC here? Now I see that the operators is the operators input instead of being just a circ Z, okay, gate, or yeah, operator. So Dance to circuit Keras model, 2-axis control model, circuits input, commands input, operators input. And the output is the expectation output. This is training the commands input, really. Okay, I get it. So this is training a neural network. So this is basically training that by fitting it. Okay, so this is the data set. Now we will also include the operators you wish to measure for each data point you supply for a model circuit. Operator data, commands, and expected outputs. 0, 1. It's a really small data set, I see, okay. Okay, I get it. So, converted tensor, the operator data. So these are the operators, the X and the Z. And then the commands are set it to 0, set it to 0. Okay, I get it. So the commands, the thing here with the net is that it translates a command into a set of rotations. That's what it's learning. So the command is either 0 or 1. And that's going to kind of correct. And so the data points here is like 0 is the expected value 1, and 1 is expectation value minus 1. Training. Now that you've in your inputs and outputs, you can train once again using Keras. Yeah, there's a lot of stuff that I don't really know about, but I think so. Now it's training. And now we are plotting. So what have we got? Okay, cool. There's a bit of a bump in here, and then it learns. The loss function has dropped to 0. The controller is available as a standalone model now. Call the controller and check its response. To each command signal, it would take some work to correctly compare these outputs to the contents of the random rotations. So the controller is available as a standalone model. Call the controller and check its response to each command signal. It would take some work to correctly compare these outputs to the contents of random rotations. Predict. So, and these are the parameters. These are the parameters of the rotations. Okay. Wow. That was that was a fun run. um, okay, I don't fully grasp all the details in here because I'm obviously a noob in all this. But intuitively, it's an illustrative example. Okay, I would think as a choice for a Hello Many Worlds, it's a funny choice, but because it's actually doesn't really showcase any quantum machine learning per se, but it's more classical machine learning to control and do error correction, which is fine, I guess. Uh, it's just an interesting choice. Cool. Yeah, I think I think I got I think I'm interested in definitely doing the other tutorials. Uh, it's definitely it sounds like an interesting thing. Okay, misclassification, calculate gradients. I think that's important for QAOA and stuff like that. Barren plateaus, the no, quantum CNN, quantum convolutional neural network. That's where it's going to be probably interesting. But it's yeah, I'll do those as well. So I'll turn that into a series as well, I guess. But it's quantum machine learning install. Okay, maybe I skipped that. Okay, I didn't read all this TensorFlow quantum design. Ah, I missed that. I jumped to the okay. I jumped to this. Okay, but it's not super extensive either. But I should probably go and read that. So I installed and I just jumped to the Hello Many Worlds. But I don't know much about TensorFlow myself, so I might actually do a bit of that as well. We'll see. Interesting. But it's been the first tutorial is pretty classical, I'd say. Uh, Classical, as in like yeah, there's a bit of a quantum circuitry and whatnot. Um, but it's more about yeah, but it does the job. It shows how the two things integrate. So I think that's interesting. Especially, I mean, I've been able to run through all that intuitively understanding it without having absolutely any deep idea about any of these concepts. So cool. Yep. Perfect.